In 1858, the pollution in the River Thames became so severe it triggered the Great Stink, an event that paralyzed the city and forced the closure of Parliament. The man tasked with fixing the crisis was Chief Engineer Sir Joseph Bazalgette. He designed a system that successfully eliminated the cholera outbreaks ravaging the population, though he did so based on the false medical theory of miasma, the belief that diseases were spread by foul-smelling air. To remove the smell from the city, Bazalgette enclosed the waste within an 82-mile underground network of intercepting brick sewers, supported by 1,100 miles of street-level piping. Bazalgette utilized innovative Portland cement and built pumping stations that resembled Byzantine cathedrals. This was monumental engineering designed to serve as the physical foundation of the metropolis. Constructing an underground system on this scale established a centralized blueprint for water management that remains the foundation of modern London today. This lock-in is also written into the micro-scale geometry of our infrastructure. In 1841, engineer Sir Joseph Whitworth standardized a screw thread with a precise 55-degree angle and rounded crests. That geometry evolved into British standard pipe threads. Because it provided a reliable seal, the design was adopted by factories and residential builders, becoming the standard connection for the global piping grid. Economists call this path dependence. It's a form of industrial lock-in, where a standard is deeply integrated and the cost of replacement exceeds the benefit of an alternative. We are now surrounded by thousands of miles of this rigid hardware, much of it buried under concrete or sealed behind walls where it cannot be easily accessed. As climate pressures strain resources, cities manage modern water crises using the fixed physical skeleton of the 19th century. We cannot afford to rip out and replace the world's underground grid. To monitor it, industrial engineers attach digital sensors to the exterior of pipes, without interrupting the flow of water inside. The primary tools for this are ultrasonic flow meters. These devices are clamped onto pipelines ranging from 25 to 1,200 millimeters in diameter. They calculate fluid speed with a margin of error near 1%, without making physical contact with the liquid, allowing for installation without shutting down the line. But the technology has a limitation. Ultrasonic signals require a full pipe. If the fluid contains gas bubbles, the signal is disrupted and scatters. With just 3% in trained air, the reading error spikes to 25%. These digital sensors are still constrained by the physical behavior of the fluids moving through the legacy pipes. This tension between old pipes and new sensors extends to the home, where aging thread standards sit out of sight behind the walls. Traditional sensors notice water pooling directly underneath them. If a pipe bursts inside a ceiling, the water is trapped behind a drywall barrier, and the sensor never triggers. To bypass this blind spot, home systems use continuous flow-based sensing. They monitor the main intake line in real time, detecting flow anomalies as small as 1 drip per second. By tracking volume at the source, this technology turns a silent plumbing network into a self-monitoring digital grid. The centralized system pioneered in 1858 was built for a different era. Today, the density of modern urban development makes expanding these underground brick tunnels physically and financially difficult, forcing a shift in how we manage water. Planners are now turning towards sustainable urban water management to adapt to population growth. This involves a strategy known as modernized mixtures. Rather than replacing the legacy grid, engineers integrate localized, decentralized systems to work in tandem with the existing pipes. This shift is appearing in new neighborhoods that use circular vacuum systems and in commercial districts that manage stormwater through local partnerships. Securing the future of our global water supply involves making these legacy pipes part of a decentralized digital network.